So how can we, and this brings us to the question on how can we measure chemical shift? And this is done by looking at the free induction decay signal. So we have our signal as a function of time is the transverse magnetization at time 0 times e to the minus I omega t times e to the minus t over t2. We've seen that previously, that expression, that's our time signal. Now let's say you have a signal that is separated by 1 ppm. So that is 1 millionth change in the resonance frequency. Would we be able, from such a signal, to be able to see a change in 1 millionth of the resonance frequency? Even if we place ourselves into the rotating reference frame where it might be easier to see that there are multiple frequencies present, we're not very good at detecting in time domain signals the change in frequency. And so here we're going to use, what is used here is the Fourier transformation. And I'll show you here the Fourier transformation of this function, but only the real part. And we'll not take the full expression here, we're just interested in the fact that the Fourier transformation is proportional to the transverse magnetization at time 0 times this function here, which is the Fourier transformation of this term here. And x here is given by the frequency, that's the argument here, minus the chemical shift, that's the exact resonance frequency of our compound, times 2 pi times t2. So what does this look like? We'll take this signal here, Fourier transform it, and we're getting this line shape here. This function here is a Lorentzian function. It has its maximum when omega is equals to delta, then x gets 0, this is maximally, and the full width at half maximum here is given by 1 over pi t2. That's the full width at half maximum of this, of the function Fourier transformed, which is also called a peak. Now the area of the resonance is proportional to the magnetization at time 0, this here. This is proportional to the number of nuclei and therefore proportional to the concentration if one can neglect the effect of relaxation, in particular here T1 relaxation. So in this case we're obtaining a signal. The area of this resonance here is proportional to the concentration. So to verify this, we have the signal at time 0 is equal to the inverse Fourier transform of g of omega, which is e to the I omega t d omega. But now we'll evaluate this at time 0 to obtain the signal at time 0. So that is the integral of this function g of omega. So that's the integral of this. That's nothing but the area of the function. And we can see that this is now the area is proportional to this term here. So it's proportional to m0 if we neglect the effects of relaxation. Now let me illustrate this with a molecule that most of us have been exposed to in their life, and that's ethanol. So ethanol is found in, among others, in nice wines. Here's its structure. It's got a CH3 group, a methylene group, and an OH group, the alcohol here. Here's the 3D rendering, here's the oxygen, here are the carbons, and in white are the hydrogens, which we are interested in. And if you now take a milliliter of wine or ethanol and you put it into your NMR spectrometer, then you observe 3 peaks, similar to here. 3 peaks here. This is the reference peak of the reference compound TMS that sets us the 0 ppm scale. What we are observing is 3 peaks. If we know there's only one compound in there, then we know we have 3 different types of protons in that molecule that are subject to 3 different chemical environments. But we actually know more, because we can also calculate the area under the curve. That is this function here. And we'll see here, this is the red curve that's just integrating from infinity to whatever frequency is plotted here. We'll see an increase here. That's the area of this peak here. Then this area here is twice as high as this one, and this area is 3 times as high here. So if we know that there's only one compound in our sample aside from TMS, and we know that the ratio is 1, 2, 3, then we know that there are 3 protons that have essentially the same chemical environment. They are to the right, so they have a lower ppm, so they are in a less electronegative environment. We have 2 protons in a more electronegative environment and 1 proton in the most electronegative environment. This is actually where we expect the OH groups to be, and so it's easy to deduce from this data that this is the most probable molecule that we are observing. So we'll stick with the example of ethanol for what is to come. There's an additional effect of chemical proximity that I want to illustrate, and we'll stick here with the example of ethanol. So we have here is, again, here's TMS, here's the methyl signal, the methylene, and here's the OH signal. Here's the chemical shift scale here in ppm, so on the horizontal axis. And as a reminder, here is the molecule that we are discussing. Now, if you look at the methyl signal, we actually see this is not one resonance, but there's 3 signals that we see. And for methylene, we see 4 signals. And what I want to explain here in the next few minutes is the origin of these extra resonances that are observed. And essentially, what they are dealing with here is a hyperfine splitting of the resonance frequency. The main mechanism that we have to consider here is that the nucleus, which has a nuclear magnetic moment, produces a very, very, very small magnetic field linked to its dipole. So we have B0, we have the electron cloud, and now if we have the same electron cloud but we have a nearby nuclear spin, then this nuclear spin will produce an extra magnetic field, this magnetic moment, that adds to the magnetic field of B0 and therefore has an effect on the electron cloud. So this additional tiny magnetic field that's linked to the dipole of the nucleus, this additional magnetic field for a spin 1/2 nucleus like hydrogen, like the proton, is either oriented up or oriented down, so this changes polarity. And this will affect the electron cloud in the molecule and therefore alter the magnetic field at a nearby nucleus. So if I have a nuclear spin here, this nuclear spin points either in this direction or in that direction. This will create an additional magnetic field. This creates an additional reorientation of the electron cloud, and at the site of the nucleus that we're measuring, it will, depending on its orientation, create a small change in the resonance frequency or the Larmor frequency. So let's say we have a nearby spin 1/2, and we'll look here at the proton resonance. So we are here interested in this proton here, and we have now a nearby spin 1/2 nucleus. Here it's pointing down, and here it's pointing up. And so therefore it produces in our nucleus hydrogen of interest, which is this guy, the electron cloud will change its configuration ever so slightly depending on whether that nearby spin 1/2 is oriented upwards or downwards with respect to the external magnetic field. And this results in a split of the resonance frequency, and the intensity of the resulting 2 peaks is exactly the same. Now, why is it exactly the same? Now remember, we had dealt with the Boltzmann distribution. So we had said the probability, whether it's up or down, that probability is essentially 50%. Well, one is 50.00001% and the other one is 49.99999%. But in terms of intensity, we don't see these small differences. So it is essentially the 50% up or down. And so therefore, the number of protons that see a spin up or the number of protons that see a spin 1/2 down is the same. And therefore, we're seeing this signal split into 2 peaks of equal magnitude, and that's called a doublet. Now for a CH2 group, so if we are now here on the methyl, we have nearby the methylene, that's 2 protons, that's these guys. And these 2 protons, we'll assume here that they are chemically indistinguishable, and so we have 4 probabilities. Up, up, down, down, up, down, and down, up. So 4 probabilities. They are of equal possibilities, four configurations of equal probability, up, up, down, down. That's easy. Up, down, and down, up, we cannot distinguish them. They give, because the two dipole fields of the two protons in the CH2 group cancel each other. So up, down, or down, up will produce the same change on the electron cloud. And so we have a triplet peak with a relative intensity ratio of 1 to 1. We're here observing 3 protons, but the next molecule that this interacts with has 2 protons, so we have 4 possibilities. 1, 1, and 2. That's the up, down, down, up. Now at the CH2 position, if I look at the protons that are here, they are seeing 3 protons from the methyl. 3 protons. So 3 protons, and they are, because the methyl typically rotates very fast, the 3 protons, they are having a number of combinations. And actually we have 8 combinations. We have up, 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 down, up, down, up, down, up, up, down, down, up, down, up, down, up, down, down, and down, down, down. So if you count this, this was 8 possibilities, and so we have a quartet. Up, up, down, up, down, up, and so on. They are indistinguishable. Same thing for the other cases. They cannot be distinguished. So this gives us a quartet, a resonance, which is split into a 1-3-3-1 intensity structure. So to conclude here, in the case of ethanol, we see 3 peaks. We have already a good idea that there most likely are 3 protons in the same chemical environment. But what this kind of splitting tells us, indeed, whatever is in here is close to a CH2, and whatever is in here is close to a CH3. And from the relative intensity 2 to 3 of the entire area, 2 to 3, it is easy to deduce that the molecule that one observes here is indeed ethanol. So I want to give here an example, and that is phosphorus spectroscopy. Well, phosphorus spectroscopy was actually the first application of strong magnetic fields to living humans. There was an interest in looking at phosphorus metabolism, phosphate metabolism in the human brain as well as in muscle. So these were the first in vivo applications, and I want to illustrate here the type of information that one can get. So this is a phosphorus spectrum, and this is taken from the brain region here indicated in yellow. One observes the signal due to phosphocreatine. We have phosphomonoesters such as phosphoethanolamine and phosphocholine. These are membrane anabolic compounds. Then one has glycerophosphocholine and glycerophosphoethanolamine, breakdown products of lipid metabolism. And then we have adenosine triphosphate. I presume you're all familiar with ATP, its structure. So we have adenosine triphosphate, so we know there's 3 phosphates in it, and indeed we have 3 resonances. The alpha is the one that is closest to the ribose. This is the alpha, this is the beta, this is the gamma. And we can observe 3 peaks related to ATP. And what we can also see here is the splitting. Here, this tells us that there's a nearby phosphorus relative to this. Relative to this peak is a nearby phosphorus, and if we can see here, it's a 1-to-1 structure. It's not very good signal-to-noise ratio here, but it indicates itself. And so we see that this must be linked to 2 phosphates nearby, and indeed this is the beta, the middle one, which sees this one and this one as well. We also have inorganic phosphate, which is resonance 24, which is this peak here, and dinucleotides, NAD or NADP, whether it's with the H or without the H, the dinucleotides contribute to this signal here. So these are the compounds that can be observed. They are linked to a large extent to cellular energetics. What is also measured is intracellular pH from the position of this peak, creatine kinase activity by measuring the conversion between phosphocreatine and ATP, and ATPase by measuring the conversion of inorganic phosphate and ATP. These are reactions that can also be measured. So this is an example of what the information that is obtainable and can be done. Here's the example of phosphorus. Like I mentioned, phosphorus, for historical reasons, was the first nucleus to be studied in vivo.